Okay, so on Monday we have a midterm exam. So I'll talk about the exam. All right. Okay, and then there was a little application of the Metropolis algorithm that I thought was really cool, and I wanted to do today, but I'm going to spend some time. Up on Piazza, I saw some stuff that I thought, well, maybe I should spend some time doing clarification and maybe, yeah. So I'll do a little explaining, and then we'll push the little demo until after the midterm. But I think it's cool. So, all right, let's. Okay, so one problem on the exam will be kind of a Bayesian inference, and you'll use a model with a conjugate prior, right? And we have already done a few examples in class, okay? So an example from class was the binomial or Bernoulli model or Bernoulli distribution. With a beta prior, okay? And then in homework for problem 1, there's an exponential distribution with a gamma prior. Okay. And so on the exam, you'll have something similar, probably not exactly the same, all right? The exam will be something similar, probably not exactly the same. Okay, and basically the idea is, all right, you will get data that will come from some distribution that comes from and except but you do not know the kind of the parameter that defines the distribution. So in class we had the example of having the bucket, and we observed some M&Ms. Some were red, some were green, but we didn't know the proportion that defines the bucket. We don't know what proportion in the bucket are green. Okay, so you'll be given kind of a prior distribution for the parameter. And then and you will find a likelihood function for the data of a parameter. So basically, you treat the data as fixed, for this likelihood function. And then you multiply the likelihood by the prior, and this will give you something proportional to the posterior. And then, then you'll, because it's a conjugate prior, the posterior is in the same form as the conjugate prior, so then you'll kind of rearrange terms to find the true parameters of the posterior distribution, okay? Rearrange or to find the kind of parameters of the posterior. Okay. Does that make sense? Are there any questions on this? Okay, so that'll be one problem. All right, and then okay, another problem will be a Metropolis algorithm problem. And we'll do a Metropolis algorithm for a discrete distribution. Okay, and again, this will be similar to the island hopping example. Similar, but not exactly the same, right? So, I will provide a target distribution, target discrete distribution. And then you will use the Metropolis algorithm to figure out the complete transition matrix P. And then, yeah, and that's going to be the bulk of the problem, and then maybe I'll ask you to do some multiplication with this transition matrix. Okay. So in class, we found the kind of we have a 7-island example, right? And so our transition matrix P is 7 by 7, and we found the row for island 4, and I think also for island 0 and 7, or island 1 and 7. Okay, and then in the homework, in homework 4, you find the entire matrix. Okay, so on the test it's similar, but it's different. It's not going to be the same, all right? But just, all right, similar but different. To this thing of having a discrete distribution, right? So you can, you could frame any discrete distribution into kind of this, like an island example, okay? But maybe the configuration of the islands won't necessarily be the same, won't necessarily be a line or something like that. So, okay. All right, is that okay? Any questions here? Okay, and then we'll have a Metropolis algorithm for a general distribution. Okay, and basically I will ask you to do 2 manual iterations of the Metropolis algorithm. Okay, and so for each iteration I'll provide basically 2 random numbers. Probably from from our unif, okay? And the first number will be used to figure out where to go, where to propose, right? So we use first number will be used to figure out what value to propose. Okay. So, people are asking, is this cumulative? It's not cumulative in that these are going to be kind of the 3 topics covered, all right? But, going from a random uniform to like a random value from a proposal distribution, that maybe that incorporates a little bit of past knowledge, right? Okay. First number will be used to figure out what value to propose, and then the second number, use the second random number to decide whether to accept or reject the proposed value. Okay. And so, in this case, I will tell you the target distribution. And I will tell you what to use for the proposal distribution. Okay, and so this will either be, and the proposal distribution could be a simple distribution, like I don't want to give too away, or it could be a normal distribution. And if it's normal, I will provide, if it is normal, I will provide a z table so you can go from our unif to our norm, right? So if you're given the z table, which is pretty much the which is the CDF of the normal distribution, you can use inverse CDF, right, with the z table to go from random uniform to random z, right? So like if your random uniform is 0.5, your random z would be inverse CDF. If I give you a random uniform value of 0.5, your random z would be 0, right? And then if I give you a random uniform 0.975, then your random z would be 1.96, right? So you could do that, right? Okay, and that would be pretty much it. So you use the whatever I give you for the to propose a value, and then with your proposed value, you'll check the ratio, probability of proposed versus probability current, decide whether to accept or reject it, and then you go from there. Okay, does that make sense? All right. Okay, and that will be pretty much the exam. So it covers, I don't know, a little bit of Bayesian stuff and the Metropolis algorithm stuff. Make sure we get a grasp on that. Okay. Are there any questions? Yes, question. Yeah, okay, so you just need to find something, you just have to make sure it's proportional to the posterior. Where are my notes from today? Okay, so, you would multiply the likelihood times the prior, and that will give you something in the form of the posterior. It's just going to be proportional to the posterior when you multiply the likelihood times the prior. Now, if we're using a conjugate prior, then let's see. So if we have like the beta distribution, okay, when you multiply the likelihood by the prior, you're going to get something in the form of this, and you'll just be missing this normalizing constant, okay? But if you just say, well, I know it's going to be in the form of a beta distribution, then the normalizing constant's taken care of for you, okay? Same with the gamma distribution and whatnot. I guess we can take a look. I wanted to do a little bit of clarification, but I don't know if that makes sense. So if you do the likelihood times the prior, you get something that's proportional to the posterior. And then if you say, okay, well, my posterior is in the form of a beta distribution, and I rearrange the terms so I can say I have this alpha and this beta parameters for the beta distribution, then we could just say the posterior is a beta 6-5 distribution or something, and that will take care of the normalizing constant. Maybe? Yeah. Okay. Yeah. Here, why don't we we'll do an example, and I'll try to make sure we're on good understanding here. Okay. Any other questions? Yes.
Problem 3, third one,
Uh-huh.
you said the substitution, and then we just use one of the second R units to check whether we accept or reject.
Yeah, so I'm going to have you do 2 iterations manually of the Metropolis algorithm, okay? And so each iteration requires, there's 2 random elements in each iteration. One is the random proposing of a value, okay? So you're going to use RUnif to propose a new random value. And then the other will be to accept or reject it, okay? So if I'm giving you 2 iterations, you're going to get a total of, I will provide you 4 random numbers, okay? So you'll use the first one to propose, the second to accept or reject, and then you'll do it again. And you'll use the third one to propose and the fourth one to accept or reject. And that's going to apply for two iterations of this, okay? And this is a problem where if you mess up the first, then it'll mess up the second. So I'm going to put heavier weight on the first part than the second iteration, if that makes sense. Okay. So you're doing the same thing twice, but there's the first iteration of the Metropolis algorithm will be weighted heavier than the second iteration. Okay. All right. Well, anyway. Okay. Let's try. I also on Piazza. You know, to put this delicately, there were some misunderstandings, and yeah, some of the student answers were. Well, I want to provide some clarity. So let's try to clear up some misunderstandings, okay? And I hope this helps, okay? And I apologize if anything was unclear in the beginning. So one thing is when we talk about a likelihood function, this is a function of the parameter. This is a function of the unknown parameter. And when we do our likelihood function, we will treat the data as fixed. Okay. So, for example, in one of the problems, we said we had 10 at-bats, and we had 4 hits. Okay. And and we asked, find the likelihood of the data. Find the likelihood function of this data. Okay, and so we assume each observation is IID from Bernoulli, right? And so that means the likelihood is just going to be the product of each observation's probability. Okay. Okay, so we have, we've got theta is equal to the probability of a hit, and 1 minus theta will be the probability, I guess, of a miss. And if we have four if we have 4 hits, we would have theta times theta times theta times theta times 1 minus theta times 1 minus theta times 1, minus theta. And this would become equal to theta to the 4th times 1 minus theta to the 6th. Okay? And this is our likelihood function. The likelihood function over the parameter theta is equal to theta to the 4th times 1 minus theta to the 6th, and this is defined for 0 less than theta less than 1. Okay. And so this is, a function of the parameter theta. Which is, the probability of a hit. Okay. And which is the same thing as the probability of our data given the parameter theta. Okay. Right, and the likelihood does not need to integrate to 1. It's just the likelihood of this realization of the data. Okay? I guess it is the probability of this particular realization of data. So it's, what is the probability of getting this exact data if my theta, if my parameter, unknown parameter, had this value, or if it had this value or something, okay? All right, is this okay? Okay, and then in our case, we have the prior distribution. Is, it could be really anything. It could be some distribution. And in our case, if we want a conjugate prior, the conjugate prior is the beta distribution. And I think what we used is we used a beta 81-219, okay, which is proportional to some constant times theta to the 81 minus 1 and 1 minus theta to the 219 minus 1. Okay. So, there we've got probability of theta being some constant times theta to the 80th times 1 minus theta to the 218. Okay. And this beta 81-219, this was this kind of just expresses our knowledge of baseball, that batters are very unlikely to have thetas over like 0.4 or thetas less than 0.2. Okay, this was just to kind of express our prior beliefs about, based on our knowledge of baseball, right? That you're not going to have somebody with a batting average of 70%. Okay. And then, okay. And then, so now the posterior, so the prior is p theta, right? Okay, and then the posterior is proportional, from Bayes' rule, proportional to the likelihood times the prior. So we have probability of theta given the data is proportional to the probability of data given theta times the probability of theta, okay? This is the likelihood, this is the prior, and we do that. So we have the probability of theta given the data, this being our posterior, is proportional to my likelihood is theta to the fourth times 1 minus theta to the sixth. This is what we found earlier. That's my likelihood. And then the prior was, you know, some constant times theta to the 80th times 1 minus theta to the 218. Okay? So, you know, whatever it is, I can, because I've got the proportional thing, I can just ignore it. And I can say we're proportional to theta to the 84 times 1 minus theta to the 224. Okay? This is what we have. All right. And what we know is that the beta distribution is in the form constant times theta to the alpha minus 1, 1 minus theta to the beta minus 1, okay? So we know our beta distribution is in this form, and is our posterior distribution in this form? It is. Our posterior distribution is in the form of a beta, and it's just that alpha has to equal 85, and beta has to equal 225. Okay? So our posterior distribution is in the form of a beta distribution, where with alpha equal to 85 and beta equal to 225. Okay? And so we could just say the probability of theta given the data is equal to a beta distribution of 85, 225. Okay? And that will take care of any kind of normalizing constant for us, because we know beta distributions are proper PDFs that integrate to 1, okay? Because the beta distribution, once you give it the terms A and B, you know, whatever parameters, shape parameters it takes, you know, the formula for the constant takes care of whatever is necessary to make it integrate to 1. Okay? This constant in the beginning, or in the equation of the beta distribution, okay, because we got it's here, it's x, but you know, x to the alpha minus 1 and 1 minus x to the beta minus 1 divided by some constant. The only purpose this thing serves is so that the thing integrates to 1. Okay, and we don't have to worry about it. It's taken care of us when we say it's a beta distribution with 85, 225. Does that, I don't know, does that make sense in terms of, you know, when we have to worry about the constant? And the answer is, if you've got a conjugate prior and you can express your final thing, so we say we know it's proportional to this thing. This thing is not a PDF, okay? This thing does not integrate to 1. We need to have some kind of constant to make it integrate to 1, and so we have to express this we say, well, we know a beta distribution is a proper PDF and it looks like this. Can I get this thing to look like this? And the answer is yes. This thing will look like this if alpha is 85 and beta is 225. Then the beta distribution looks exactly like my thing with a proportionality constant, and then we'll know it integrates to 1. Is that okay? Yes, question.
So the concept of there, do we solve it? Is that the beta to divide it by and then it integrate to 1 and then
Do you need to figure out this number? No. Okay, if you tell me it's the beta 85 comma 225, okay, then that means we can plug it into here, and then we could plug in 85 and 225 into here, and this, whatever this turns out to be, will be the constant that we need. But I don't know what that is, and I don't think my ordinary calculator can do that, but who knows? Yes. Yeah, you might. So in homework for problem 1, maybe I'll kind of help us work through homework for problem 1, and this will give us some sense here. Okay, and again, problem 1 it's not this problem, but has data coming from an exponential distribution with unknown parameter lambda. Okay. All right. So y comes from the exponential, which has PDF lambda e to the negative lambda y. Right. So that's the PDF of an exponential distribution. And then the conjugate prior is the gamma PDF, is the gamma function, or gamma distribution. Okay, and its PDF is this constant, beta to the alpha divided by gamma of alpha. This is just a constant. And then the important part is it's x to the, so if we look up gamma distribution, okay, it's right here. There's 2 parameterizations of this, but we're going to use this one. Beta to the alpha over gamma alpha, x to the alpha minus 1, and e to the negative beta x. Okay, x to the alpha minus 1 times e raised to the negative beta x. Okay, and because we're modeling lambda, all right, we are modeling lambda, so I'll replace x, the symbol x, with lambda, because that's what we're modeling here. Okay, so I'm going to just come in here and I'm going to just make this lambdas. Okay, and this, so we have a PDF over lambda here. Okay, all right, and so let's just say let's say lambda comes from our prior distribution. Prior distribution for lambda is going to be a gamma distribution with shape parameters 5, 2. Okay, and so my PDF is going to be some constant times lambda to the 5 minus 1 for e to the negative 2 lambda. Okay, so that's my prior distribution for for lambda, okay? All right, and then let's say my data for y is 0.4, 1.2, and 0.4. Okay, so I just have 3 data points, okay, 3 observations. Right, and I want to know, after I observe my data, what is my posterior distribution, right? Okay, so let's figure out what is the likelihood function of our data. Okay, so we treat the y as fixed, okay? Our observations are fixed, and the thing that's unknown is our parameter lambda, right? So y is fixed, and then lambda is unknown. Okay, so I've got the likelihood of my data as a function of lambda is going to be basically the product from 1 to 3 of the PDF, lambda e to the negative lambda y. Okay, so this is, my y is coming from this distribution. So each observation has this probability, okay? So this will be the product of lambda e to the negative lambda times 0.4, okay? Multiplied, the next observation is lambda e to the negative lambda times the probability 1.2 times lambda e to the negative lambda times 0.4. Okay, so that's the total probability of my data. Okay, I treat my 3 observations as fixed things. Okay, and so I can combine these, and I'll have lambda to the third and e to the negative, and I add all of these up, and I think I get negative 2 lambda. Right. So this is my likelihood. My likelihood of lambda. So this is the likelihood. Okay. So far, so good. So here's my prior, here's my likelihood. Okay. So my prior is lambda comes from gamma 5, 2, which is the form lambda 4 e to the negative 2 lambda, and then my likelihood is equal to lambda to the third e to the negative 2 lambda, right? So I multiply these together, so my posterior is proportional to the likelihood times the prior. So I will get lambda to the third e to the negative 2 lambda times the prior lambda to the fourth e to the negative 2 lambda. And here I get lambda to the 7 e to the negative 4 lambda. Okay, that's what I have. So my posterior is proportional to this. Okay, can I write the posterior in the form of a gamma? Okay, gamma is in the form of a constant times lambda to the alpha minus 1 and e to the negative beta times lambda. Okay, and the answer is yes. Okay, yes, let alpha equal to 8 and let beta equal 4. Okay, and then so now we have our posterior is equal to a gamma distribution with alpha equal to 8 and beta equal to 4. Okay, and that will take care of the constant, which is beta to the whatever it is divided by gamma, beta to the alpha divided by gamma of alpha or something like that. Okay? Does that kind of make sense? All right. Oh, there's another thing I wanted to clarify, but we're going to run out of time. And that was stuff about confidence intervals and credibility intervals. And a common question that kept popping up is it okay that my confidence interval looks so different from the credibility interval? Okay? And the answer is yes. That was the whole point of the exercise. Okay? The whole purpose of those series of problems was to illustrate how the confidence interval and the credibility interval are different. Okay? A confidence interval only takes into account the data that you have observed. So if you've only seen 10 data points, okay, your standard error on that data is very big, and so your confidence interval is going to be quite large, right? So if you see somebody go up to bat 10 times and you get 0.4, okay, or like if you draw marbles out of or M&Ms out of the bucket and you draw 10 of them and you get 4 of them are green, according to classical statistics, it is possible that the bucket is 70% green, okay? And that because of random chance, you only got 4 green, okay? That's entirely possible. That happens with classical confidence intervals. However, the credibility interval takes into account your prior knowledge. And your prior knowledge says, you know, in baseball, the player with the highest batting average of all time had a batting average of 36%, okay? So there's no way that a batter can have a batting average of 70%, okay? According to statistics, yes, random chance, you could have 70% and get only 4 out of 10. That's possible. But with Bayesian statistics, we say, you know what? My knowledge tells me that there's no way a person can have a 70% batting average. Therefore, when I make my credibility interval based on the beliefs I have prior to seeing the data and after seeing the data, my credibility interval is still saying, I'm pretty sure the guy's baseball batting average is going to be something between 20% and 35%, okay? That makes a lot of sense, okay? But yeah, if you didn't take into account any other outside information, then yeah, could the probabilities be anywhere from 10% to 70%? Sure, that's possible. But but in Bayesian statistics, you're taking into account your prior knowledge. And as the amount of data you gather grows, then your reliance on your prior knowledge becomes smaller and smaller and smaller, okay? So as you gather more data and you see 5,000 hits or 5,000 at-bats and 1,750 hits, then that gives you strong information that this is a player with a very high batting average, and thus your credibility interval will be much smaller at a high area, and your confidence interval will also be very similar, much smaller at a very higher area there. Okay, so that was the whole purpose of that thing. Was to illustrate kind of the difference between the confidence and the credibility intervals. Okay, we'll end there. Good luck as you guys study for the midterm. Have a great weekend. Wish your mothers a happy Mother's Day, and we'll see you guys on Monday.